Hi, my name is Manish Gupta, and in this video, I'm going to talk about XTR, which stands for Contextualized Token Retriever. Okay. So let's get started, and let's start by first understanding what is dense retrieval, what is multi-vector dense retrieval, how does ColBERT work, and then we'll get to how does XTR work on the next slide. Okay. So dense retrieval is something as against keyword-based retrieval. So remember, traditional retrieval basically works by matching keywords using TF, IDF similarity vectors, cosine similarity, and so on. As against that, dense retrieval basically does query and document matching in the embedding space. Now, you could basically do dense retrieval using single vector retrieval methods, also called as dual encoder methods, where you take the query, you encode it using some embedding generation method. You encode the document also using the same method, same encoder, and then you compute cosine similarity and rank based on the cosine similarity between the encoded query and the encoded document. Okay. Now, to be able to do these kinds of things, you take all the documents in your collection, you index them into an approximate nearest neighbor search index, and then at runtime, when a query comes in, you embed the query using the encoder, and then you use the maximum inner product search on top of the approximate nearest neighbor search index so as to return matching documents. Okay. Now, what people have found is that it is much more accurate to do multi-vector retrieval. So multi-vector retrieval models, they basically work in the token space. So they actually use multiple dense embeddings for each document and query, right? For each document and query. So let's say our query Q basically contains n tokens, document D contains m tokens, right? So then what these methods do very generally is basically compute the similarity between query Q and document D using this formula, right? So essentially, in some ways, sort of computing weighted similarity between every query token and every document token, right? So essentially, A here is a binary matrix. So A is a binary matrix, n cross m. So it can every cell can take a value 0 or 1, indicating whether the ith token, ith query token is aligned or related with the jth document token or not, right? So, and Pij essentially indicates similarity between the ith query token and the jth document token. Okay. So now ColBERT specifically is a method which basically sets this Aij as follows. So Aij is equal to 1 only if, considering all the document tokens 1 to m, right? For the ith query token, Aij is going to be 1 only if it has the maximum similarity with that jth document token, right? So that's that. So basically saying for every query, you actually identify the best matching document token and set that Aij equal to 1. And therefore, in case of ColBERT, basically use the same formula and normalize it as well with respect to number of query tokens, because normalization typically helps you to train in a more accurate manner, right? But the main idea is that rather than using Aij, you can basically now say that, hey, I'm trying to find out that particular document token, which is the maximum similarity given any query token I, okay, or Qi. Okay, so basically now, given this optimization function, you essentially train ColBERT using a cross entropy loss over in-batch negatives. So which basically means that you take a batch of B documents, D1 to DB, right? And it basically contains one positive document given a particular query. So, and what you do is essentially, compute cross entropy loss as follows, where, of course, you want to give higher similarity, ensure that there is high similarity between the query and the positive document, and low similarity between the query and all the documents. Okay. So that's that. Now, considering this entire architecture, the way the inference works is basically in 3 steps. The inference in ColBERT works in 3 steps. When a query comes in, you essentially figure out query tokens. Let's say our query has 2 tokens. Okay. And then you try to retrieve those document tokens, let's say top k dash document tokens with highest similarity. So let's say k dash is 3. So you basically retrieve this, this, and this, and you said, oh, these 3 tokens are highly similar. Okay. Now, but you need to actually compute this QI transpose DJ. And therefore, what you end up doing is to basically end up getting the entire document. So essentially, to be able to compute the entire QI transpose DJ, you essentially gather or load all the document tokens for all candidate documents. So there are two candidate documents here. Of course, document one has like these four different document tokens, out of which only two are in the top K dash. But you basically gather get all of those document tokens as well. This is an expensive step to load all the document tokens across all candidate documents in RAM. Okay. And then the third thing is scoring and refinement. So you actually compute this score. So essentially you compute QI transpose DJ for both of those documents. And then, once you have those scores, you basically rank in terms of top key and then return to the user. Okay. So the three-stage inference pipeline, which is basically cumbersome and not very efficient. So what XTR does is to make it efficient. So basically, rather than having token retrieval, gathering, and scoring, basically XTR completely avoids the gathering phase. And XTR only has token retrieval and scoring. Now let's try to understand how does XTR make this possible. Okay. So XTR basically, what does XTR do? So XTR basically at train time does in-batch token retrieval. So essentially, for any query at train time, you essentially try to figure out B matching B, M matching tokens from every document in the current batch. So you basically have a query and you have basically the current batch of documents. You essentially try to figure out M highest matching tokens from each of those documents. So basically ending up with M into B tokens. Okay. Now, and then what XTR does is basically define Aij equal to 1 only if, only if those tokens are within top K dash in terms of top K in terms of similarity. Okay. So basically what XTR does is to consider token similarities within D within a particular document only when they're high enough to be retrieved within top K from a batch. So there's a batch of documents, you basically got like MB tokens and they're fighting with each other. From those M into B tokens, what you do is to basically just take top K matching tokens and essentially give them, you call them as positive. So so that's how Aij hat is defined. We're using hat just to differentiate XTR from ColBERT. Okay. Now, that's that. So the idea is that and this is basically the objective function for XTR. Notice that this is very similar to the one for ColBERT, except that here, in ColBERT, essentially we had in fact, more or less, it is basically exactly similar, except for the normalization factor for that matter. Okay. Just the normalization factor differs, and also the way you define a hat differs, basically, right? So what is the normalization factor? Well, there could be certain query tokens for which there are no document tokens at all in the top K, right? So in which case, basically, you consider only those query tokens for which there is at least one document token in the top K. Okay. So that is that. Now, essentially, the way inference works differs significantly in XTR. So the way you do this is you basically given a particular query, you get top K dash documents with highest Q transpose D for every query token. So you take a query token and, there are query tokens from 1 to N. For each of them, you basically get top K dash documents with highest similarity. Okay. So, and then the scoring, essentially, rather than doing the scoring on the entire set of document tokens, you actually just do the scoring on top of those tokens, which basically were in the top K dash. Okay. Now, the point is that this avoids you from loading these extra tokens in those documents, and therefore makes the process way more efficient. Okay. Documents are scored solely with the retrieved token similarity. However, there is a little bit of a mismatch between train time and the test time. At train time, over iterations, what happens is that you end up having really relevant tokens, relevant documents in the batch, which basically means that for every query token, you actually have some sort of non-zero similarity with every document token. And you sort of use that so as to compute these objective function. Okay. So therefore, what XTR does is to essentially also incorporate this missing similarity imputation. And the way it does is basically using this revised objective function. For every query token, what it does is to basically, if there was a particular, if there was a particular document token, which was, if there was a document token, which was there in the top K dash, then it would just use the similarity with that document token. Else, it would else what it does is to basically use a default similarity value. Okay. So MI is basically the default similarity value, just that because no document token was within the top K dash for this particular query token, you basically use a default MI value. And this default MI value is basically not in the top K dash, and therefore you basically replace it with an upper bound to what could be the similarity of this query token with any other token in the document, right? So now to be able to compute that exactly, you would really need to load all the document tokens, which you want to avoid. And therefore, this upper bound estimate is basically fixed as Mi is equal to Qi transpose dk dash, where dk dash, dk dash is the K dash the document, matching with the query. So remember, for every query token, you retrieved K different document token, K dash different document tokens from the approximate nearest neighbor search index. Now, you basically just use the similarity with the last retrieved token, document token, to define this upper bound. Okay, so that is how you make up for the missing similarity for given any particular query token. Okay. So either you have an actual similarity with some document token, or you basically, have an estimated upper bound similarity. Okay. So now the biggest selling point of XTR is, of course, it can basically, it is much, much cheaper at inference time. So compared to ColBERT, XTR is 4,000x cheaper in terms of floating point operations required, right? Also, the recall, as you can observe, in fact, this kind of computation, although it looks like it's an approximation, it actually helps. On BEIR benchmark, they actually observed that the quality improves for the dense retrieval. Recall at 100 basically rises from 64.5 to 68 on 13 different BEIR benchmark datasets that they measured on. Okay. So this leads me to how does XTR perform? Well, they fine-tune XTR models. They basically initialize XTR models from T5 base encoder and T5 XXL encoder. Right. And they fine-tune them on MS Marco dataset with a fixed set of hard negatives from Rocket QA dataset. Okay. They do evaluation on multiple different datasets, in-domain evaluation on MS Marco test set itself, 13 different zero-shot BEIR datasets, 12 different datasets from Lotte benchmark, right? 4 open domain question answering datasets, including entity questions, natural questions, trivia QA, and Squad. Right? Stanford question answering dataset. Okay. They also do multilingual evaluation on Miracle dataset, which consists of retrieval tasks in 18 different languages. So I don't have all the results here, but I've plotted the results for these question answering data sets, these entity QA, natural questions, and then trivia QA and Squad, right? And they do comparisons with several other retrieval methods, including the standard, age-old BM25 method, but they also compare with the popular DPR method for dense retrieval and with other dense retrieval methods, right? Including ColBERT. And what you observe is that XTR base and XTR XXL provide the best results across various methods in terms of passage retrieval accuracy at top 20 and as well as at top 100. Okay. Now, on the right side, what you see is the results for the 13 BEIR benchmark datasets. And as you can observe, they basically do 2 kinds of experiments. There are baselines which basically use 1 retriever per domain for each of those domains. And then there's of course, that's not scalable at all. But there are also these methods which basically use 1 retriever for all, including XTR base and XTR XSL. And as you can observe, on average, XTR base gives you that, and XTR XSL gives you that, which is both of them are actually better compared to their equivalent sized baseline methods. Right. Similarly, you can observe that on Lotte, 12 data sets, you basically observe that typically XTR basically does better on most of them, compared to other baselines. Okay, in terms of so here basically it shows for the BEIR benchmark, it basically shows nDCG at 10 values here, and these ones are basically top 5 retrieval accuracies. Okay. So in summary, in this video, I talked about multi-vector retrieval, which basically uses query and document token representations for effective information retrieval, and it basically involves 3-stage inference. In the first stage, you basically do token retrieval and gathering and then scoring. But then what XTR did, XTR basically stands for ConteXtualized Token Retriever. What it did was to score documents solely based on the retrieved tokens, which is also optimized during training with in-batch document tokens, right? While doing so, it basically avoids the gathering step completely and does scoring only on cached similarity values, which were already computed in the first phase. Okay, so that basically ensures that XTR is multiple order, better in, requires multiple orders of lesser floating point operations compared to ColBERT, and it also establishes state-of-the-art accuracies on zero-shot IR benchmarks like BEIR, Lotte, and so on. Okay, reduces inference flops by a significant amount. That's it for this video. Thank you for watching. Hope you liked it. Connect with me on my LinkedIn or look at my research on my homepage.